Okay, next let's talk about curl fields. So this is perhaps a little bit more complicated, but we'll figure it out. So here's the idea. Stokes' theorem is going to provide a way to evaluate flux integrals by turning them into a line integral, but I can only do this in special cases, similar to the case with gradient fields. In this case I need a curl field, and I'll explain what that is in just a minute. So suppose I want to find a flux integral through a vector field G, and I know something about this vector field G. In particular, I know that I can find another vector field F such that the curl of F is equal to G. So notice what happens in this case. I want to evaluate the flux integral of G through some surface, but if G is equal to the curl of some other vector field F, then this statement, this is Stokes' theorem. Stokes' theorem says that I can turn this flux integral into this line integral over the vector field F. Okay, so the key to all of this is to be able to find that vector field F. That vector field F is called a vector potential. So the gradient field had a scalar potential, the curl field has a vector potential. And I need to find a vector field F that is going to give me this statement. Okay. So here's what we'd like to do. If I'm given a vector field G, I'd like to be able to find a vector field F whose curl is G. Okay. So unlike with scalar potential functions, vector potential functions are not as easy to find. And so in many cases, it would be nice to know beforehand if it's even worth looking. That is there one? There's not always going to be a vector field F that satisfies this condition. And so is there a way to know? And the answer is yes. So if I'm given a vector field G, and again there's this vague nice condition, it has to be defined everywhere I'm interested, and if when I take the divergence of G, I get 0, then it turns out that in fact G is a curl field, and I should be able to find a vector field F. Well, there is a vector field F. Whether or not I can find it is unclear. But if the divergence of G is 0, then G is a curl field, and hence has a vector potential function F. Here's an example. So I'm given the vector field 2xi plus 3y minus z squared j plus x minus 5zk. And I'd like to know, is it a curl field? That is, I'd like to know, is there a vector potential function? So notice it's very easy to determine whether or not it's worth looking for a vector potential. I take the divergence, so I simply take the derivative of 2x with respect to x and get 2, the derivative of 3y minus z squared with respect to y and get 3, and the derivative of the k coefficient with respect to z and get minus 5. And notice that in fact this is 0. Okay, so G is a curl field. The answer is yes, it is a curl field. And so then we can try to look for a vector potential. Okay, as I said before, now we're going to try to find this vector potential, and this is not necessarily that easy, and it's a little bit of fishing. So here's what I'm going to do. I'm going to write down a little bit at a time pieces from the formula for the curl. So this piece is the coefficient of I in the curl of F. So I'm thinking of F, the vector field that I'm looking for, as F1I plus F2J plus F3K. Okay, so the I coefficient of the curl of F looks like this. It's the partial of F3 with respect to Y minus the partial of F2 with respect to Z. Okay, so I'm just going to try to build this function F in the easiest way that I can and just hope that it works. So I'm going to try this. I'm going to try F3 is equal to, well, I want its derivative with respect to y. I'm going to hope that the derivative with respect to y is just going to be 2x, as simple as that. So in F3, I'm going to put a 2xy, and then there might be some extra stuff, some function that's only a function of g or x and z. So when I take the derivative with respect to y, I'm going to get 0. And I'm just going to hope that this is going to work with f of 2 is equal to 0. Okay. So since I've let f2 be 0, or at least I'm hoping that this is going to work, I'm going to look at the next coefficient that has an f2 in it, because this derivative will then of course be 0. This is the coefficient that goes in the k component of the curl. So this needs to match x minus 5z. So I need 0 minus the partial of f1 with respect to y to be equal to minus y times x minus 5z. So notice if I take the derivative of this with respect to z, I'm sorry, oops, did I make a mistake? I guess, well, if I take the curl, it should match that. Okay. And if I take the derivative, here's what I want to say. If I take the derivative of f1 with respect to y and take into account the negative, I want to get that. Okay, I'm sorry. I want this to be equal to x minus 5z. So, of course, what I really was trying to say is that I need f1 to be minus y times x minus 5z. I'm sorry for the confusion, so I'll say it again. If I take the derivative of f1 with respect to y, I'm going to get this piece, if I take into account the negative, and that needs to match with that component of g. Okay, so far I've built f3 and I've built f1. And then I can take into account the middle term, and that looks like the partial of f1 with respect to z minus the partial of f3 with respect to x. That should be the j component in the curl of f, and so that should match the j component of g. So I need this to be equal to 3y minus z squared. Okay, I've already defined essentially f2, f3, and f1, and there could be some other bit over here, but I'm going to try to just play with g of xz to make this work. Okay, so what I need to figure out, can I make this happen? So I need to calculate the partial of f1 with respect to z minus the partial of f3 with respect to x, and see if I can pick g that will give me this as a result. Okay, so the partial of f1 with respect to z, notice there's a 5yz term, so when I differentiate with respect to z, I simply get 5y minus, I'm going to take the partial of f3 with respect to x, so I get minus 2y minus the partial of g with respect to x. Okay, so you can see it's not too bad. I want to compare 3y, and over here I have 5y minus 2y, so that's good. And then I need minus z squared. Did I make a sign mistake somewhere? Maybe not. I want minus z squared to be equal to the derivative of g with respect to x. So it's boiled down to that. I need the partial of g with respect to x to be minus z squared. So that is, I need g to be equal to minus xz squared. Okay, so I'm sorry, I did make another mistake. This minus should be a plus, so that should be plus z squared, and g should be xz squared. Okay, so here's what I get. I take that g, and I go back here, and I modify f3. f3 is 2xy, plus I now know what g is. g is xz squared. So I've got all the pieces. I've got f3, I've got f2 is simply 0, and I have f1 is minus y times x minus 5z. If I take those three pieces and I plug them into f, that is the vector potential. Okay, I'll finish by just giving you a hint of the one other problem that's on the pre-class homework assignment set. The question asks you to write a given vector field as a sum of a curl-free field and a divergence-free field. So that is, I want to take a vector field and write it as a sum of two vector fields, one whose curl is 0 and the other one whose divergence is 0. Okay, so here's the hint. It's easier to think about divergence first. Think about what needs to be true for a vector field to have zero divergence. Pull off those pieces from the original vector field and write them into a divergence-free piece. And then what's left over, hopefully, is curl-free. And look at it and check it. Calculate the curl of what's left over. And then think about for just a minute what it is that makes that curl-free vector field, in fact, curl-free.